Welcome everyone. Thank you so much for joining us today. Thank you a lot to IEEE, in this particular the New York City chapter for Vehicular Technology Society, for welcoming us today so that we can demonstrate and talk about our technology for the very first time actually. It will be the very first time that we talk about the principles and what's the tech behind our underground GNSS. I won't be the only one talking today. So Aurélien Corsakisok, who's the head of global deployment for underground GPS at Syntony, will join me for Q&A. And if you're wondering who I am, my name is Rémi Tellier. I'm VP of Sales and Marketing for North America, based in San Francisco. And yes, so we're going to talk about GPS today. And in particular, we're going to talk about extending GPS coverage underground. So first, I'm going to go through a very quick introduction on why do we even need GPS underground. And then we're going to talk about how to simulate a GPS signal, either one GPS signal or even multiple at the same time, and what does it take. Then we're going to deep dive into the setup in tunnels for the two different configurations that we developed, the zone-based positioning technology and the continuous navigation technology. We're going to finish up with a couple of real-life use cases in order for you to understand how it could be useful. So first thing first, GPS. Well, GPS is the technology that has one very big particularity. The technology gets instant adoption both by people and machines, and it works with most devices we already have, and this without any software update or hardware update. And by that, I mean that everyone is using GPS with Google Maps, with Maps on iOS, but also professionals with P25 or Tetra. So it's a standard, and because it's a standard, most safety and many comfort services rely on GPS now. And I'm not talking only about underground, I'm talking about everywhere. And it's used mostly for two big things: people, location, and navigation. And that applies to workers, emergency services, and users. But also for things, for trains, for vehicles, also cars, machineries, and even drones. The only problem with GPS right now is that the signals are sent thanks to satellites, and they don't go through objects. So there is no GPS underground. And in the same time, underground navigation is critical. So especially in subways, in road tunnels, and in mines. And that's exactly what we're going to talk about today. So the technology I'm going to talk about has been deployed in 8 countries already, listed here, in all those different applications. So extending GPS coverage underground, that actually comes from space on our side. It's derived from a technology that we've been providing to the space industries for the past 5 years and the fruit of 15 years of R&D. And you're going to understand why it's so much work. So there are two big parts in our technology. The first one is using GNSS simulation. And the second part is leveraging the existing infrastructure, whether they are typical antennas or leaky feeders, in order to extend GPS coverage to road tunnels and subways. And if you don't know about all those words yet, don't worry, I'm going to go through it. First part, GNSS simulation. What is GNSS simulation? So first, GNSS is a generic word for all satellite-based navigation systems. And all those systems, such as GPS, are working in a very simple way. They are sending a stream of timestamps that receivers collect in order to compute their position. If we want to simulate this, there are 3 things to take into account. The first part is the trajectory of all the satellites. The second part are the signals that are emitted. And the last part, and that's the tricky part, it's everything affecting them. And if we are able to recreate all of that, we are able to recreate the electromagnetic field that a GPS receiver needs in order to compute its PVT, which is position, velocity, and time. So if we have a quick look from one single satellite, what does that mean? It means that you have the satellite and you need to know its position on orbit. You need to know to simulate its speed, its atomic clock error, because even though those are very precise clocks, they still have error. And on the message part, on the signal part, you get the navigation message, including time. I said earlier, it's a stream of timestamps. So time, the almanac, which gives a course position of satellites, and the ephemeris, which is the orbital and clock correction. Again, we said that clocks are not perfect. This message is then modulated in phase and quadrature and emitted on the L-band at 1575.42 megahertz so that your receiver can get it. That's pretty straightforward, but if you really want a simulation that works, you need to take into account anything affecting the time of arrival on the receiver's antenna. And that includes Doppler effect, relativity effect, Earth rotation, and ionosphere and troposphere delay. Imagine that this is just for one signal. A real simulation takes, for GPS only, 31 satellites positioned 12,550 miles away, with signals going at the speed of light and satellites going at the speed of around 8,700 miles per hour. We need 4 inches accuracy on the satellite part, meaning that you have a satellite over 12,000 miles away from you, but you need to know its position with a 5 inches accuracy. Also, you need 5 nanosecond precision on your clock. And the final part, just to give you a couple of examples of what it takes, the model we use, the JGM3 Earth gravity models, and they are up to the 30th order. So that's a lot of computing happening here. There are 2 steps in the simulation. You have first to simulate all the satellites in orbit, and then you need to see which signals would be received by a position at a given time, and select which signals would be received and generate them. So there are really 2 parts of it. And the time precision is extremely important because GPS is all about timing. So the way that this is done is by generating 100 million of IQ samples. Those are part of the signal every second for each signal. So that's 1 sample every 10 nanoseconds that needs to be computed and generated. Time is extremely, extremely important. And just to give you a tiny example, if we end up being 10 nanoseconds late due to anything affecting the computing, we would get a 10-bit error on the receiver. So this is why we need extremely precise equipment. So we have a unit which is based on an industrial PC set up in technical rooms, and that includes 2 big parts. So the first part is a dedicated computing unit, which obviously takes care of our software, but has also a very powerful microprocessor backed with FPGA. And then we have a very performant front end, and it has the particularity of being able to have 12 output of signal per unit, with each output generating 4 or more satellites at a given time. So that's a lot of computing. Then you get obviously over-the-air update and monitoring for all those devices. So this is what it takes on the simulation part of our technology. So we said earlier that it's all about timing. Well, the reason behind this is that GPS is strictly based on time of arrival. Angle of arrival doesn't matter. So as long as each signal is respected and the delay in between the signals are respected, any receiver listening to a combined signal wouldn't be able to make a difference in between the real satellites or something else. And they will be able to compute their position perfectly. one unique source can be enough if it's well done. That's exactly what we do. We provide the same service as GPS satellites, combining multiple satellites at the same time. And we have two versions for this, the zone-based and the continuous high precision technology. Before telling more about the two different technologies, let's talk about the setup and the infrastructure behind this. If we have a look at a tunnel, and what we do is we are leveraging the existing infrastructure in order to send our signal. When it's already in place, we're using leaky feeders. Leaky feeders, they are cables which are used by GSM, 4G, P25, Tetra, and they are acting as antennas leaking signal. Because GPS is a very low in power signal, it doesn't interfere with any telecommunication signal already in those leaky feeders. To give you a bit more perspective, inside the metro, this is the kind of infrastructure you get. You have already antennas everywhere. They are used for all the telecommunication technologies I said earlier. And you get technical rooms in which we set up our equipment, and this equipment is linked through existing optic fiber network into those antennas. So now let's talk about the zone-based positioning and how it's set up. Well, we have this unit which is doing all this simulation, combining all those signals. This unit can generate the signal for a given position. And this position, we choose it to be at the center of the leaky feeder. In that way, when the signal is sent into the leaky feeder, wherever you will be under this leaky feeder, and what you will see is that you will be in the zone, meaning at the center of that zone. And this is how we do it for zone positioning, and that's how we started with GPS underground. We can also use omnidirectional antennas in order to achieve the same result. Now, we took this way further. And this technology, we demonstrated it a couple of months ago, and it was a world premiere. So we said earlier that if we have one source can send the same signal as multiple satellites at a given time. Well, the truth is, we can also separate this into two different sources. And if we do that, and if those two sources are well synchronized, it will still be the same thing for a receiver. So that means that we can use one output of our unit, send it to one side with one particular position, and we can send also another signal with a different position, the other half of the satellite, to the other side of the leaky feeder. And when you do that, you are able to recreate an electromagnetic environment in which the GPS receiver just works. And the reason behind this is it's using the delay of propagation of the signal inside the leaky feeder in order to compute its position. So you get a position all along the leaky feeder. And this is here the principle behind our technology. We can obviously do the same thing with directional antennas, always using the delay of propagation. So that's it. That's basically our technology. So we're on one side using GNSS simulation, which requires a lot of computing and a very high time accuracy. And on the other side, we're using existing infrastructure underground in tunnels and in subways in order to recreate either a continuous navigation system or a zone-based positioning system. So that's how we generate GPS underground. So now I can take a couple of minutes to tell you a bit more about the applications behind this. And we said earlier that it's unleashing underground all the safety and comfort services based on GPS. Because yes, GPS is used by many people and for many different applications outside. This can now be only used in the exact same way inside. So to give you a couple of examples, I'd like to start with E911 or Enhanced 911. This technology is in place and is the technology that police and all the emergency services are using to locate you when you call 911. The way it works is when you take your phone and you call 911, your GPS position will be automatically sent to the dispatch center. And that's already in place. We have nothing to do with this. The only difference is that when you're outside, it works. With GPS underground, that also works inside. Another example to keep everyone safe is to allow firemen to navigate and fight people in smoke. If you have a fire in a tunnel, firemen needs to localize where people are, and then they need to navigate through smoke, and any navigation technology is always very helpful. Also, because GPS is a standard, anyone can use it. So anyone can use it to find the exits, for instance. To give a couple of use cases, again, here, we're building the infrastructure, and then based on this infrastructure, many companies are already providing technical applications for very various use cases. But just to name a few, navigation in road tunnels. I don't know if that happened to you already. Happens to me for sure quite often. I take an underground tunnel, there is an exit underground, and I miss it. I miss it because I don't know where to turn, because my GPS freezes. Well, that's a solution for that. Also, navigation for people within stations and subways. You can also get alerts when you arrive at the right station. We're talking about also location-based payment for people using metro. You can also use it to study underground traffic, and most importantly, allow police and the army and the firemen to navigate and operate underground too. Because at the end, this is a safety thing. It's also used a lot to keep workers safe, meaning when you have a train coming and workers working on the way, well, you want them to know it, and you want the train driver to know that too. And that's actually a more tricky problem than it seemed to be. And GPS is a solution for that too. Another thing is to send a rescue team as soon as a worker is not responding. There is a myriad of applications, and that's the strength of the system. Not implying any particular software, any particular devices, and having a very various crowd using it for their own challenges. So telling trains to slow down and stop when workers are on the way, find non-responding workers, save time before restarting operation post-incident, because if you know where things are and where people are, you can save time. Localize train to advise passengers. Use also as backup to localize train in case of their navigation system just don't work. Also localize trains used for maintenance, which are not using navigation system that typical trains have. It can also be used to spot maintenance location on the tracks so that they can come back and fix it. And localize any object or vehicles on the ways. Here I'm talking on the ways, but that also applies to road tunnels where people need also to operate. So that's it. We're bringing real GPS, real signals to the inside world. We're doing this for everyone's safety. And that was a sneak peek into our technology. And I want to thank again IEEE for giving us the opportunity. Aurélien will join me now for the Q&A session.